it's very straightforward. What the situation is that we have a equation like this. Okay? We did, yeah, I mean, you guys have seen this. We did this in polynomials and so on. We have an equation like this. B and C are some numbers. And also, obviously, some two numbers have to be given, right? Otherwise, fine. Let us say that A1 and A2 are given some number. A1, A2. Obviously, now you can put values and find A3, find A4. We have done examples of this. A Fibonacci sequence made that B and C is -1, -1. We have done other examples, right? Like an plus an minus 1 plus an minus 2 is equal to 0. We saw there was a cyclic pattern. So we have done examples of this kind of sequence. Okay? Is there a polynomial satisfying, blah, blah, blah. But today we just want to solve this completely. Okay? Right. So without going into too many, as I said, motivation, let's just do it as an exercise in induction. So the claim here is that En is like a sum of geometric progression. Maybe let's do it in this way. So if you suppose have this, right, and if you suppose make a guess, so you make a guess. So okay, let's say that An is equal to some. So is it? If you say that An is, let's say, some sort of a geometric progression. Okay? So there is some initial A and R to the power n. Is it fine? Or is it too abstract? Should I put some numbers? So we take An as this. So this is like a guess. Okay, so you guess that this is a solution for a minute. Then what can we say about the A and the R? Right. That's the point. If this is a solution, then you put it in this equation, right? And let's see what happens. So we have this. Right? Then An minus 2 is. Okay. Let us just simultaneously also do it for the Fibonacci so that it's not too abstract. Okay. You have the recurrences like this. Okay. And you have no way, I mean, let's say you don't know how to solve this. All you know is that A1 equal to A2 equals to 1. But you don't know formula. You can, at every step, you can put values and find, but you don't know formula. What do you have? You say, okay, let me make a guess. It's like a growing very fast, like a geometric progression. Let me make a guess. So let's guess that this is the solution. Now my question is, what can you say about the R? At least on the Fibonacci side, please tell me. What can you say about the R? Then we'll get this. What can we say about the R function? There is dots to cancel. We cancel those things. And then you get this. This is implied, and this implies this. I mean, R is not 0, certainly. That's not right. I did the solution, but that is not what we're interested in. Use this. A also. So what is R? It's like we are guessing the solution looks like this. We are putting it in the equation and we are extracting information about the solution itself, about our candidate solution. So what is R? You can solve the quadratic. Hello.
Yes, sir.
Right. So what does R come out to be?
R has to be a natural number.
No,
Or
there is
just a
no.
positive number.
It can be anything. Right? It can be negative also.
Sir, I'm getting 1 plus root 5 by 2 and 1 minus root 5.
Yes, the Fibonacci thing. Means we got this in the similarity question also last time, right? But yeah, the point is that this is the two possible values of R. So see, it's not complicated in the sense you have a recurrence, you're guessing a solution, and then you're finding information about the guess solution. R has to be, if any R is possible, it has to be this two. There is no other R possible. Okay. Now, on the left hand side simultaneously, you will get that R is, R is the roots of the quadratic. R is alpha and beta, where alpha and beta are the roots of this quadratic, right? That is what you will get. It's the same thing. So this is 0. So when you cancel the a and the r to the n minus 2, you will get the quadratic. Its roots will what r will be. Okay. Right. So then, if you look at the Fibonacci side, what do we see? We see then that the possible solution, right, is like, and also you see the a is not, nothing can be said about the a. We cannot say anything about the a. So we will just put some a1. We don't know. A1 we have already used. So in place of a, we'll just put some lambda 1 because we don't know. Right? So one solution is like this, right? But then this is also possible. Are you guys following? This is what I had guessed for my solution. Now look at this. This is a very special type of equation. I mean is following. A very special type of equation in the following sense. Slightly changing the topic. Look at this. Suppose I tell you, suppose I give you this. Okay? X plus y equal to 0. Okay. So can you tell me a solution to this? Any, it doesn't have to be integer.
So minus 1 and 1.
Yeah, minus 1 and 1. Yeah. Any other solution? Maybe just take minus half. If these two are solutions, what does it mean? It's a very silly thing I'm saying, but this is a solution and this is a solution. You see, if these two are solutions, then the sum is also a solution. The sum of these two solutions is also a solution. Right? You can add these two component wise and this two component wise, and it will again be a solution. Right? Okay. So I mean, any solution, if you have two solutions, then their sum is also a solution. Sum meaning that adding it component wise. Right? Okay. So that is one of the things. Here also, you see, similar thing will be true. So in what way am I saying this? If you look at this, let's say that a times r1 to the power n is a solution. Let's say this is a solution, meaning it satisfies this equation, recurrence. And let's say there is some other solution, two solutions. Okay? Then the sum of these two will also be a solution, right? You can just check. Right? So if we have, r1 to the power n minus lambda 1, so r1 to the power n minus 1 minus lambda 1. This satisfies. This one also satisfies. You can simply add them, right? Component wise. But now we can just add. Just add these two. I mean, they will still satisfy the same. I mean, as easy as it looks, right? They will still satisfy the same equation. This will again, again you can write this, and then you can write this. It will again satisfy, right? If you have two solutions, their sum is also a solution. The difference is also a solution in the same way. Okay. So what is it fine so far? Making sense?
So that's true because it's equal to 0, right?
Yes, that's the main thing. It is homogeneous. It is equal to 0. Otherwise, it is not true. That's why these equations are so easy, right? Right. So the point here is that you guess two solutions, and then you can take sum of solutions, difference of not product, right? Difference of solutions. You can multiply one solution 2 times and multiply one solution 3 times. That will also be a solution, right? So they all of them become candidates. And so the point is that from what we have guessed so far, from what we initial guess we started and the possibilities we got, finally we can say that these are all. I put a plus there now. I just put a plus there because, as I said, sum is the solution. This is our candidate, a very general candidate. This is our candidate. Now, how do you find the lambda 1 and lambda 2? Yes, any question?
Sir, I was asking that lambda 1 and lambda 2 are just variables, right?
So far, they are variables, right? How do we find them? We find them by a1 and a2. Put n equal to 1, you get 1. Put n equal to 2, you get two equations in lambda 1, lambda 2, and from there you find. Okay, the same process. I mean, so the point is that this does not prove that this is a solution, right? I mean, this doesn't prove that this will be a solution. This proves that this is the candidate for the solution. Am I correct? Because at no point have we proved that this is the solution.
Yes.
Right. So we yes, that's right. So this is a candidate for the solution, and no, but we have sort of proved it also. So does this satisfy the equation? Right. So the point is that now we just have to show that this also satisfies this equation for the correct values of lambda 1 and lambda 2. Okay. Right. That's so. Let's forget about the general case for a minute. That will just be the same. Right. This is our guess. It's a very, very good guess. Now we just want to show that it also satisfies this equation, right? But see, that is very simple. All you have to do is you have to put it in and check. But let's do it because otherwise it's not clear. It might look a little long, but see, I just put it there, and you will kind of feel it's a repetition, right? But you see, it is needed because we have to use the fact that we have found the correct values of lambda 1 and lambda 2. So let's see. So if I put this here, I will have to show that it works. 2 and minus 1. I did this with other people also, but I did it. That was a completely different. It was a different way we did it. Okay, this is going out of the page. Right. Don't worry. I mean, it looks like I'm writing too much, but that's because we are sort of not using good notation. Otherwise, one just uses alpha beta in place of this root 2 and root 5. That's okay. That's minus and minus. And we want to check if this is 0. I mean, that's so. Let's not write equal to 0 for now. We want to just check if this is 0. But what does it come out to be? If you just take the terms in common, right, then you will see that it works. So what I'm saying is you take this in common, and then what do you have? You have this. So you get, I might be stretching it more than it's needed. Yeah, but let's see. See, we want to show that this is 0. So we just do the calculations. And then there is the lambda 1. Okay. Right. Yeah. But then you know that this is 0. Right? Because this 1 plus root 5 by 2 satisfies that quadratic. Right? Which means that it is 0. Am I correct? Yeah. It is 0, right? And similarly, this one is also 0. And minus 2, similarly, we know that this one is also 0. Okay. Right?
So that equation is nothing but when you put the value, like when you put the root in place of x, right?
Yes. Yeah, exactly. That's what this expression is. And that is why it's becoming 0. The lambda one is not a problem. You can take it out. Right? Yeah. So then, but then the problem. So then what we have proved is that this is a solution. Is a solution. Right? This satisfies this. Right? Once again, satisfies this. But there is a problem. I mean, it is fine. I mean, as far as we are concerned, we know what the procedure is, right? You see this equation, you look at the quadratic, x square plus bx plus c, find its roots, and the solution will look like this: lambda 1, times alpha to the power n plus lambda 2 beta to the power n. Lambda 1, lambda 2 you can find from the initial values. But so this satisfies this equation. So it means that this is a solution. Now we force the, yes, there is no problem. It, is there any, seems to be any problem? No, right? Because we have strictly shown that this satisfies this equation. So this is a solution. Now, if you tell me that A1 and A2 are 1, then using that, I will be able to say something about lambda 1 and lambda 2. Okay, but whatever lambda 1, lambda 2, it will still satisfy this equation. So there is no problem. So far what we have proved is the following, right? That if you have this equation, right, then the solution is this sum, this. I'll just finish it. Power n, this, where the lambda 1 and lambda 2 can be found by A1 and A2. Let's say using A1 and A2, you can find lambda 1. And obviously this alpha and beta, what are they? They are roots of this x square plus bx. That's it. This is the picture. I just wanted to discuss this technique because this theorem is very, very important. The final result at least. Okay. Now you can, I mean, let's just quickly do one example, right? Otherwise, how would you know if you understood this? I'm writing the quadratic. So an minus 5n minus 2 plus 6 an minus 2 equal to 0. So let's try to find, let's say that a1 and a2 are 1. It doesn't matter. So we want to find the formula. So what do we do? As a process is very easy, but don't go by the easiness of the process, okay? It's easy, it's good, but that will not help you too much. It's nothing very nice to just know the steps, but you should understand this proof because a lot of questions will be based on that. That is really what understanding something is. This is just you take the quadratic, find the roots, okay, and then you know the solution is fine. This, what is lambda 1, lambda 2? We'll put n equal to 1. 1, put n equal to 2. Find it later. Find the lambda 1, lambda. This is nothing, right? This is just silly. It's easy. Okay. But here is this fine? Do you guys understand this? Is it?
Yes.
Okay. This is simple.
Sir, in of an we put x as the variable, right?
Yes. In place of an, we put x as the variable. Yeah. Yeah. So just you can understand how this is formed. This is called the characteristic polynomial, but it doesn't matter. You know how to go from here to here. But this is, yeah. The question is for homework maybe is that maybe let me just put it like this. Okay. Given, yeah, first you do it as a calculation, then later on we can see. A10 equal to 1 and A20 equal to 1. So now I'm trying to present that given any two random values in the sequence is also enough for you to tell the sequence completely. They don't have to be the starting values actually. We feel always that I have to know the starting value to know the rest of the sequence. Well, that is good. But in fact, if you think about it, any two values will be enough. But even if you don't think about it, you can still find it using this formula. So, yeah. So try it. Given this, find an. And you can keep the same equation. You can take other equations for your own fun and try it out. So we use the linearity, right? We use that if you have two solutions, if you can guess some easy solutions, then you can combine them to form the harder solution. That's the rough idea, and that is very important. Okay. But then you have these kind of questions, okay, where there is a problem, or maybe should I stop? And maybe I'll stop. Right? We will see this later. So what happens if there's only one root? Okay, so maybe it's a homework. Try it. So you can take any, maybe as a easier homework. This also we saw in the polynomials class. Probably not even. Try this. What if we want? Try these two, and let's stop for this. Okay, so we have a few things to try. So the next class is so tomorrow 9:30 p.m. as I said, and I said it's fine. Okay, so then yeah, happy puja.
Tomorrow 9:30 or 9 o'clock?
Oh, sorry, it's 9 o'clock. Yeah, tomorrow 9 o'clock. As I've said, what I'll and but Friday 9:30, don't forget, because that's a non-standard time. Friday 9:30 p.m. That we will do this fast, try to solve the problem. The practice, please find the time, use the time. All right. Good night.
Bye.
Bye, sir.